Let's have a look at linear functions of random variables, and in particularly how we can find the expected value and the variance of such linear functions from the expected value and the variance of the random variable we begin with. So the idea is as follows. I have a random variable. She's given to me. So that means that I know whether it's discrete or continuous, I know the range of it, and I know the probability mass function or the probability density function. So since I know f of x, I can calculate the expected value of x, and I can calculate the variance of x using the formulas that we have seen previously. But from this random variable, I can also create a new one. Let's just say random variable, and a new random variable is denoted by y. But this new random variable is simply a function of the old random variable x. If this g function is linear, if it's linear, then we can write it like this: y is equal to some intercept plus some slope times x. We could also think of nonlinear functions. So if y was, let's say, x squared, it would be a nonlinear function of x. Turns out that a really important problem in probability theory is to find the expected value of this new random variable y, given that I know the expected value of the random variable x. Fortunately, we have a very nice formula for this. The expected value of y is simply equal to a plus b times the expected value of x, which we have calculated previously. And a and b can be any constants, and it's always going to be true. So the way we typically think of this when we work with probability theory is the expected value of y is the expected value of y, which is defined as, I just replace now y with a plus b times x. And in the next step, the terminology we use is that we say that the expected value goes inside linear functions. It goes inside linear functions. So we take this e thing on the a term and on the bx term. The expected value of a, that's the expected value of a constant, is that same constant. And then we take it inside b times x, so the result is this. We have to be careful remembering that it only works for linear functions. So if y is a nonlinear function of x, and I want to find out what the expected value of y is, then this would be wrong. I can't do this. Expected value of y, I replace y with x squared. That's fine, that works. I can't move this one inside the nonlinear function. So this does not turn out to be the same as expected value of x squared. We have a similar formula for the variance of a linear function. So again, if y is a linear function, a plus bx, then we have the following. So I'm going to do that, it's important. The variance of y will be b squared times the variance of x. The terminology we typically use when we handle these cases is as follows. Variance of y is the variance of y is a plus bx. We say that we can take the variance inside, and so we look at the variance of this one first. The variance of a constant is 0, as we talked about in the variance section, so we'll have 0 from that one. The variance of b times x, this is where you need to just to remember one thing, and that is whenever you take a variance of a constant times a random variable, the constant can go outside. Let's write it like this. This constant can go outside, but we have to square it. It's a really important rule to remember. Whenever you take a constant outside the variance, it must be squared, so it's b squared, variance of x. So going back to the notes, we have the following setup. We have a linear function of our random variable x, and we have the following result. The expected value of this linear function is a plus b times the expected value of x, and the variance of a plus bx is simply b squared times the variance of x. Although it's not that hard to prove these from the definitions of the expected value and the variance, you have to do it first for the discrete case and then for the continuous case. I think there is much more intuition in looking at an example. So here I have my starting random variable x. It has an expected value of 2.4 and it has a variance of 0.84. I'm now going to create a new random variable y, which is going to be a linear function of x. So let's set up some constants for the linear function, a and b. And again, it's not going to make any difference which numbers you pick, it's going to work no matter what. So let's pick the intercept to be, I don't know, 2, and the slope of this linear function to be 3. So now we can create our random variable y, and y is just going to be this linear function of x. So whenever x takes the value 1, y will take the value a plus b times 1. So just transform each possible values. So when x is 1, y is, well, a is in k, and we need to use the dollar sign so it doesn't increase. The intercept plus the slope, no, it's k $2, plus the slope, which is k $3, times the x value, which is a2. So when x is 1, y is 5. And the slope is 3, so x increases by 3 units for each unit that x increases. So it must be 8, 11, and 14. So these are the possible values of y. What are the probabilities? Well, if you think about it, y takes the value 5 whenever x takes the value 1. And x takes the value 1 with probability 0.2, so the probability that y will take the value 5 must be the same, 0.2. So we can just copy these probabilities. They will be the same. So let's now do all these other things so we can get the expected value and the variance. So I'll put these two here, and they will now represent the expected value and the variance of y. Starting with this one, just replacing this with y times p. Then the expected value of y is just the sum of these guys. So y has the expected value of 9.2. Well, according to this result, the expected value of y on the left hand side second bullet point should be the same as a plus b times the expected value of x. So let's calculate that. Let's put here a plus b times the expected value of x. And according to the formula, that should give us exactly the same result. And indeed it does, so that confirms this formula for this example. We can also check the variance. Just copy these guys like this. change the reference to the correct expected value, because this now need to refer to H11, the expected value of y, like this. And then we can get the variance simply as the sum of these ones. So y has a variance of 7.56, larger than the variance of x. That makes sense because the y numbers are much more spread out than the x numbers. According to the second formula, the variance of y should be b squared times the variance of x. So we can check that, equal to this squared, not to the 3, but squared, multiplied by the variance of x. And we see that we do get the same result. And it doesn't make any difference how you change this. If I change the intercept to -2, the expected value and the variance will all be the same. If I check this to -3 or to 4, whatever, these will always be the same, confirming this really important result. We can also see that if I try to do a nonlinear function, then this will simply not work anymore. So instead of doing a linear function for the y, let's say I do a nonlinear function, such as squaring the x value. So if I do this squared instead, then it's 1, 4, 9, 16 instead. Oops, like this. Then you can see that the formula doesn't work anymore. The expected value, this is the correct value, that is the expected value of y. This one, calculated from the expected value of x, is no longer applicable. So for a non-linear function, we have to go through this long process of actually figuring out the expected value and the variance of y ourselves.